Hello and welcome to another technical demonstration video by Computer Modeling Group. Today's video will be on the geochemistry modeling aspects of the software. My name is Marco Misenta and I'm a reservoir simulation engineer at CMG. So the modeling options that we're going to look into today are built into CMG's fully compositional simulator GEM. GEM has had a kinetic reaction model for a number of years, which is particularly suitable for mineral precipitation and dissolution reactions. In this model, a reaction rate for a mineral reaction is calculated as a function of a number of experimentally derived parameters, particularly the reactive surface area in units of square meter per cubic meter, which characterizes how high is the connection between the area of the mineral and the rest of the aqueous environment. So the higher this parameter, the faster the reaction. The second parameter is the rate constant of the reaction, which is proportional to the activation energy divided by temperature in the exponential factor here, and you will recognize here an Arrhenius type model for the rate constant, which we adopt also in CMG. And finally, this term 1 minus Q divided by equilibrium constant, where Q divided by the equilibrium constant is the activity product over the equilibrium constant, which is called the saturation index. And this term defines the direction of this reaction. When Q is larger than K, we'll have precipitation occurring. In the opposite case, dissolution will take over. Another modeling option for chemical reactions is instead the equilibrium reactions model. The equilibrium reactions model is most suitable for aqueous reactions, not involving minerals, because these reactions are normally very fast. So for an aqueous reactions, standard reaction is written here, we would equate the equilibrium constant of the reaction, as I said, a function of temperature, to the activity product itself, which is the product of the activities of the products in the numerator of this fraction divided by the product of the activities of the reactants, all the activities raised to the power equal to the stoichiometric coefficient of each species. Alongside this model, more recently, an equilibrium model for mineral reactions have been also designed in GEM. This is slightly different in that we still calculate a rate of reaction, which in this case is based on the product of the mass of water in each cell times the tuning factor, which is controlled by the user, times the factor 1 minus saturation index, which again will determine the direction of this reaction. We mentioned activities. Activity modeling in GEM is done by calculating the activity coefficient by a number of possible modeling options. The activity is the activity coefficient times the molality for each species. Molality, of course, being moles over kilograms of water. The activity coefficient is either set to 1 in the ideal solution option, which basically assumes that the activity of each species is the same as the species molality. But for real solution cases, we normally adopt other activity modeling tools like the B-dot model, which is the default in GEM, the bi-Huckel model, and more recently, GEM added the Pitzer model, which is suitable for high salinity environments. I'm going to move over now to a demo where I'm planning to show to you how to quickly add geochemistry modeling options into an existing GEM model. The GEM model under consideration, our base model, will be a model for CO2 storage in aquifer. The model is a box which represents our aquifer with an injector for CO2 defined in the middle. Two options characteristics of CCS have already been added to the model: the CO2 solubility in brine and the water vaporization, which is a process that can occur when injecting at high gas rates into an aquifer. These can generate a vaporization of CO2 of H2O near the well, which we want to account for. Alongside these options, now we want to add geochemistry for the purpose of modeling basically two things. One is we want to add the mineralization process for CO2, meaning that some CO2 can be mineralized in the geological unit of interest, and the other process is the salt precipitation, which is mostly linked with the water vaporization process. As water is vaporized, we may expect an enhanced precipitation of salt near the well, and we want to quantify that. I'm going to assume that this reservoir is a classic reservoir, so the minerals are more characteristic of a classic formation. I'm going to choose then a calcite, and I'm going to have to input this equation for calcite in the simulator. And I'm going to assume also kaolinite is another mineral present in my formation. This is the formula for kaolinite and the reaction. For these two reactions, I'm going to opt for a rate-dependent model. So I'm going to use the kinetic model. And then I'm going to add another reaction. This one is not related to mineralization processes really, but it's more related to the salt precipitation process. So we want to model precipitation of sodium chloride, halite, in the system. And for this specific reaction, I'm going to use the equilibrium model instead, based on the assumption that this reaction is supposed to be a very fast reaction. Alongside these mineral reactions, I will have to select a number of intra-aqueous reactions, the minimum set of which for a specific case of CO2 injection will be these three reactions. The first one, very important, will model the chemical reactivity of the CO2 molecule with water once CO2 solubilizes in water. The second one is the typical water dissociation reaction, and then the last one dissociates HCO3 minus into CO3 2 minus and the hydroxide ion. Let's have a look then at the model opening a builder. CMG is a preprocessor. This is the base model for CO2 injection in the aquifer. I'm going to just check my well, show you that the injected fluid is pure CO2. The well is open for a year, and the simulation is carried through for 200 years. I'm going to close the well section and navigate now to the components section of Builder, into which I'll be able to change the components by adding the ions and the minerals that are needed for modeling geochemistry. This has now been automated by going to the Process Wizard option under Components. This Process Wizard contains actually a number of guided tasks, one of which is geochemistry, but we also have guided tasks for other features, including CCS. In this case, the CCS model is already set up in part. I only need to work on geochemistry, so I will select the option, add or modify geochemistry only. So I'll go to the next step. Here is the point at which I can input my reactions. The reactions can be read directly out of a number of publicly available geochemical databases. The first here on the top is the MINT-EQ database, which was published by Allison and Brown, coming from the Environmental Research Laboratory in the US. We have the FreeQC database. We can connect via this button to a user-defined database as long as this database is written using the FreeQC keyword syntax. And at the bottom, I've got the default database the builder by default connects to, which is the Wallery database. From the blue section, I can access all the intra-aqueous reactions of this database. So I'm just going to quickly pick the reactions that I showed you on the slide before. And like I said, these will be equilibrium reactions. In the yellow section, I can select my minerals. So one was calcite, and then kaolinite, which I'm going to select from this drop-down list. And you can see that the default in the wizard is to select a TST model. TST stands for Transition State Theory. This is the kinetic dependent model that the GEM uses by default, that was built into GEM. And as you can see, it comes with the definition of the laboratory-derived parameters that we saw on the slide as well, the reactive surface area, the activation energy, and the log 10 of the reaction rate constant. Anything can be changed here. If you have your own laboratory data, you can override this data coming from the database. You may have noticed that actually I don't have that many reactions here. The database is actually far more exhaustive than this. If I wanted to see more reactions, I could go and check the option Show All Reactions. That will show the full range of reactions available. Here I still have halite to choose, and I'll just add halite. But as we said, we would like to model the halite reaction as an equilibrium reaction rather than a kinetic dependent reaction. So I'm going to change the option from TST to equilibrium. I can now move on to the next step, which consists in characterizing the formation water and the original mineralogy of the rock. In the yellow area, I've got the formation water properties, the pH, which would be 5. And then depending on the ion selected, I've got the list of ions that I need to initialize my water with. So the Ca++ ion, I've got 500 ppm, parts per million is the default unit in the wizard. Then I've got sodium with 138,000 ppm. For chloride, 213,000. You can see that for aluminium and SiO2, the wizard is recommended some data. Unless you have more reliable data coming from your laboratory, we would recommend sticking to these data as they come from published literature data on brine that we have input in this wizard. For the rock mineralogy, we have the volume fraction of the mineral, 0.1 for the two minerals considered here. And for halite, I will assume that there is little to no mineral at the beginning, so I will enter a very small original fraction. And I'll go to the next level. Here, I'm not planning to change the composition of the injected fluid, so I can just click Finish. And given that we've added geochemistry, we could add some more output relating to geochemistry. So I'll go to the Input-Output Control area, Simulation Results Output, and on the Grid section, I could add, for instance, Activity Output, but in this case, I'm going to focus on the mineral output, so the change in mineral moles of my three minerals, and potentially I could have, for instance, the log 10 of the saturation index if I was interested in this property as well. So I'll add this extra output, give OK to the IO control section, and now I can save this model as my geochemistry final model. Before running it, we could have a look at the model in text editor to check what builder added to the dataset in terms of keywords. The keywords will be under the component properties section, And the header keyword for geochemistry will be the geochem v2 keyword. Anything below this keyword is relating to the geochemistry properties of the model. So we have our ions with their physical properties at the top, followed by the minerals with their physical properties as well, followed by this big block of keywords, which really is relating to the reactions and their parameters. So we have three types of reactions mainly here. The reaction chem defines the equilibrium reactions for the intra-aqueous reactions happening in this model. The reaction rate TST for calcite and kaolinite will be referring to the kinetic rate-dependent model for these two minerals. And then if you remember, we changed for halite, we changed the keyword to equilibrium, and the actual keyword is reaction equilibrium MNR for mineral for halite. Running the model in Gem will obviously output our results, and I'm just going to show you the results directly here. So if we had considered the original model by itself, where we didn't have any geochemistry, all we could have output in terms of the CO2 breakdown in different trapping phases would have been the dissolved CO2 in water and the CO2 supercritical, as I see in this case. As time goes on, more and more CO2 moves from the dissolved phase into the, actually from the supercritical phase into the dissolved phase. Now, having added geochemistry, I can also plot the trapping into the mineral phase, as well as the trapping into the aqueous ions phase. So the difference between these two is one is the CO2 that's been mineralized, and the other one is the CO2 that has only interacted with water and split into the ions that we saw in the reaction, H plus and CO3 2 minus ions from the equations that we defined in this model. For as far as the precipitation and dissolution profiles are concerned, that we can have a look at the output that we asked for minerals. And for the minerals, we decided to have the output of the mineral mole changes. This is a very useful output because it gives you very clearly and very visually the answer as to the question which mineral is precipitating, which mineral is dissolving. In this case, clearly the change is positive for calcite and it is negative for kaolinite. So calcite is definitely precipitating in this model, whereas kaolinite is undergoing dissolution all the way through. We could go and do some sort of more in-depth analysis on a block-by-block basis. Like in this case, I'm showing one plane in this reservoir around the well, and I'm plotting the mineral calcite, which is basically the moles of calcite in each block as I probe the blocks around the model. And on top of that, I've also activated the output for the log 10 of the saturation index, which is a small but positive number that indicates that precipitation is indeed occurring in this block. And this also gives us a quick representation of the calcite precipitation profile on the grid around this injector well. Everything here is very homogeneous, so this pattern is very regular around the this well in this simple box model. We talked about halite as well because we wanted to see precipitation of halite. And indeed, we can see that in this plot, for instance, I'm showing a sector around the well. There's very little precipitation far from the well, but as I remove blocks and I tie down my view on the near well area, you can see that the maximum value of halite precipitated amount are indeed concentrated in the well block. And here on the side, I'm plotting the mineral halite. First of all, we can see a quick, sharp increase in mineral halite over the first section of the simulation when CO2 is injected. And this is accompanied by the decrease in water saturation, which is in part due to the augmented effect of water dry out because of the water vaporization option that is implemented in this model. And we can also check that indeed some of the water is partitioning into the gaseous phase, as I'm showing here. This is the red curve showing the gas mole fraction of H2O. So close to the well, there is indeed a enhanced precipitation profile for halite, which is indicative of this drying out effect, and so of the accelerated reaction that turns the two ions, Na plus and Cl minus, from the aqueous phase into their mineral component, halite. So this was a simple, quick model that incorporates geochemistry for the purpose of mineral trapping of CO2 and salt precipitation. And I hope this has given you a clear overview of how we can quickly and easily add multiple reactions in the aqueous phase and for the mineral phase as well into a gem model by using our interfacing builder. I would like to thank you very much for your attention today. Thank you.